Alright, so we're going to try this again. What is half-life? Half-life to me, and this is in science and things like that, you hear this term thrown around all the time, and what the heck is it? Well, half-life is an amount of time. And in this case, it's the amount of time for if something decays for it to be half of its amount. So, for instance, if I have this lump of uranium, whatever, so it's all giving off radiation and burning people and whatever. So we have this lump of uranium sitting out there on the ground, and it's decaying. It's basically blowing itself up, kind of not blowing itself up, but decaying. It's disappearing, and changing to something else, and for a certain amount of time. When it reaches half of its amount, so now we have that same material, but there's only half as much left. This time is its half-life. When will it be half as much? Okay, we deal with this all the time in our real lives, okay, whether you want to believe it or not. Half-life. So let's say you go to, and there's all kinds of formulas for half-life. Look them up. I think it's nonsense to memorize a lot of those. If you just know a few, like for instance, PERT. This is the continuous growth formula, or also the continuous decay formula. Or maybe we could just use simpler than that, the one for annual. But so this would be your amount equals P e to the RT. So that's continuous growth. If we just wanted the simple like annual rate of growth or decay, we could just use A equals A times 1 plus or minus R. Since we're dealing with decay, it's going to be 1 minus R to the T power, where T is time, A is our initial amount, and the capital A is the amount that we end up with. And, here, let's keep it the same. So this would be your principal, your first initial amount of material. Sometimes they'll use A naught there. It just depends on the textbook that you get, or whatever you're dealing with. Everything uses its own symbols. So be flexible with what symbols you use there in those places. R again stands for your rate of decay or rate of growth. They're depending on what's happening. In this case, we're doing decay. There's R as your rate of decay. So in this case, it's going to be negative R because it's decaying. So back to my example. We have a car that you go to the wherever you want to buy a brand new vehicle, and you spend $50,000 on this brand new vehicle. I don't know, a lot of money. You had a lot of cash and bought a brand new car, 50%. Well, I know that cars, for the most part, decay at a rate of 25% per year. So that is their decay rate. Their rate of decay instead of growth. So we'll just use this one for now, and I'll kind of show you how this half-life works. Well, so we want to know how long it's going to take for the car to be worth half as much. What's the half-life of this car? And so $50,000 is our principal, our initial amount. That's what we paid for the car. We want to know what its half-life is, so that would be $25,000, what it's going to end up at. And we know it decays at 1 minus 0.25, that's your rate of growth, for a certain amount of time, T. And so you just solve this baby. Now this one would probably be pretty easy to guess and check with. But we'll go ahead and isolate the exponent by dividing by 50,000. And 25,000 divided by 50,000 is 1/2. 1 minus 0.25 is 0.75 to the t power. Now, I'm going to use the natural logarithm of this to both sides to get the t out front. Again, if you're not sure what I'm doing here, go to look up videos on how to solve exponential equations. Because I'm kind of using some fancy stuff. You could use some just guess and check, like I said. But it's better to, this can give us a more precise answer for now. And so this would be t times ln of 0.75. And then we're solving for t. Well, t times natural log of 0.75, you divide by that natural log of 0.75 on both sides. And so your time is natural log of 1/2 divided by the natural log of 0.75. And so the half-life for this particular car, there we go, is 2.41, approximately 2.41 years. So in you could calculate that down to the month or the day if you wanted to. But in approximately 2.41 years, that car is going to be worth half as much. And that's a half-life. And that happens, think about your iPads and your iPods and all this technology that we're using. What's its half-life? That'd be kind of an interesting scenario. But half-lives, there's lots of drugs that have a half-life. I don't know the drug offhand, but there are many that come up with. You might end up with. You might start with maybe 60 cc's of a certain material, and after. So instead of me stuttering around, here's the problem. So if we have 60 cc's, which is cubic centimeters, of medicine, that's quite a bit, I suppose. 60 cc's of medicine on a shelf, and it has a half-life of 14 days. How much of the medicine will be left after 20 days? Okay. Well, this time I kind of gave it to you in reverse. I give you how many days the half-life is, but I didn't give you its rate of decay. We know cars decay at 25% a year on average, depending on the vehicle. In this case, we have the half-life given to us of 14 days. And I guess 25%, and before we were talking about annually. Now we're talking about, a half-life of days. So in this case with medicines and things like that, anything in nature, they decay, the model for decay for them or growth is this PERT equation, usually. And so we'll go ahead and use this. And we have, see if you can figure it out. See if you can calculate. First thing you need to find is your rate of growth, or decay in this case. So when you do this, you have 60 is what we start with. So it goes here. E to the R, we don't know the rate of decay yet, but we do know that every 14 days it is exactly 1/2. So R times 14, when we plug all that in, it should produce 30. So if you go ahead and solve this thing, and again we want to isolate that R and that exponent, so we're going to divide by 60. And so we have 1/2 equals, and hold on, stop everything. Sorry. We're going to go back. Before you just dumbly plug into formulas like I just did, you should estimate an answer. It's ridiculous not to, and I forget to do it all the time. Because, how do we know if our answer makes sense? Well, let's go through this logically. Okay, we started with 16 cc's. We know the half-life, we will have half the material in 14 days. So, you start with 60. You go 14 days. Now we've got 30. So if you went 14 more days, we'd be at 15. So that would be a total of 28 days. Well, we only want 20 days. So we're going to be somewhere in here. So I don't know, maybe we're 25 or so, or 24, I don't know, something like that. But around 24 cc's is what we should end up with. Something in that vicinity. So we had 60 cc's, then 14 days later we had 30 cc's, then 14 more days later we'd have 15 cc's. So we don't, oh, sorry, yeah, 14 more days. So 28 total days we'd have 15 cc's. So 24 is going to be, somewhere in this vicinity. I'm just guessing for 30, between 30 and 15 cc's, somewhere in there. So let's go back to our problem. Sorry, but that's important to do. So we know if we get an answer between 30 and 15, we're probably on the right track. So anyway, we divided by 16 and we got e to the r 14r. Again, that bothers me a little bit to have the 14 at the end. Use the commutative property. And then next thing you do, again, we want to isolate this r at the top, so we're going to natural log both sides. So natural log of a half, we don't know what that is yet, but we do know natural log and e, Euler number, are inverses, so they cross each other out. If you want to know why that happens, please feel free to check out some other videos, because that's not this particular video. But natural log of 1/2 equals 14r. So then we know our rate of decay is natural log of 1/2 divided by 14. Now, the answer is going to be, when you divide those out, a negative 0.0495. So again, that's not the answer we're looking for, it's just the rate of decay. But now we can plug that back into our original formula. So again, all exponential growth and decay formulas look like this. We want to know the amount. If we start with 60 cc's of material that decays at a negative 0.0495 t, and we know t. We know t as 20 days, excuse me, times 20. And you start, so here we go. This will produce our amount. So you take 60 times e to the negative 0.0495 times 20, whatever that is. But you should end up with, and I was close, but it's 22 cc's when you plug that in. And so that falls between our 30 cc's and 15 cc's for 14 to 28 days. So, hey, that looks like that's a pretty accurate answer. So, sorry, it's getting a little late. I'm probably a little random in my talking, but hopefully you got enough out of that to kind of understand half-life. And hope this helps you. See you next time, and thanks for listening.